Hello everyone, welcome to a new lecture in the series of control of mechanical systems. In this lecture, we will be discussing about sliding mode control of mobile robot. Here is the overview. We start with a brief introduction to sliding mode control or SMC, which is then followed by SMC of mobile robot. In general, sliding mode control or SMC is a nonlinear control approach which uses relay as the basic control element. Relays can be considered as the limiting case of saturation functions as shown in this figure, where the saturation becomes a relay function when the gain of this linear region becomes infinity. And as we can observe from this figure, a relay is a discontinuous control element where the output of the relay switch between minus k and plus k and can be mathematically represented using the signum function, where here u is equal to k signum of e. And in general, the control law for first order SMC can be represented as in equation number 1, in which UC is the continuous component of the control signal and the discontinuous part is defined using the signum function as k signum of s, where s is the sliding variable which is also known as the switching function. Therefore, in the case of sliding mode control, the control will switches between the value of UC plus k and UC minus k based on the sign of the sliding variable s. For more details on sliding mode control and its implementation, the lecture series on SMC can be referred, for which the link is given in the description. Next, we move on to the SMC of mobile robot. For the SMC design of mobile robot, we will be using the kinematic model and the dynamic model, for which the derivation is discussed in the previous lecture. In the kinematic model, we have three states which are x1, x2, x3, which corresponding to the error in x, y, and theta. Here, these state variables are corresponding to the error in the linear position and angular position. Therefore, in position tracking, our objective is to make the error 0, which means make the state variable 0. For that, we will be using a Lyapunov based approach for the control design. And here, we will be selecting the Lyapunov function as in equation number 4, which is a function of x1, x2, and x3. Here we can see that when x1, x2, and x3 are 0, this v of x is also 0. For all other values of the states, the Lyapunov function will be positive. Or in other words, the Lyapunov function is a positive definite function. Now we have the derivative of v can be obtained as in equation number 5. And by substituting for x1 dot, x2 dot, and x3 dot from the kinematic equation, we can obtain v dot as in equation number 6. Now in the case of Lyapunov based design, the main objective is to design the control law in such a way that the derivative of the Lyapunov function is negative. This ensures that the value of the Lyapunov function will eventually become 0, thereby the states will also become 0. Now in order to make v dot x negative definite, we have to select u1 and u2 accordingly. Here we select u1 and u2 as in equation number 7, and now by substituting this in the equation for v dot, we obtain v dot of x as in equation number 8. Here we can observe that this is a negative definite function. Therefore, if we select the gains k1 and k2 as positive, we can make v dot x as negative definite, and thereby the stability of the states can be ensured. Now for the design of the dynamic model, we will be using SMC to control u1 and u2 in such a way that u1 will be following this function and u2 will follow this function. Here we will be using SMC for designing the control law for the dynamic model, and the SMC control law can be defined as in equation number 9, where the control variables v1 and v2 are chosen as minus k1 signum of s1 and minus k2 signum of s2. Here the sliding variables can be chosen as in equation number 10, which are selected as u1 minus u1r, where u1r is defined like this, and s2 is equal to u2 minus u2r, where u2r is defined like this, where these values were obtained from the previous slide as per the Lyapunov based design. Now the simulation parameters are chosen as in equation number 11, and this figure shows the response of the mobile robot with the SMC. Here we start from the initial condition 0, 0, and our objective is to follow a circular path with radius 1. And here this black curve shows the reference trajectory and the red curve shows the actual trajectory. And here we can see that the actual trajectory is following the reference path. Figure 3 shows the time series plot of the variables, where in the first subplot we can see the plot of x1 versus time, in which we can observe that the states will be start following the reference trajectory within 2 seconds. And the second subplot shows the tracking errors, where we can observe that the errors become 0 in a few seconds. And in the third subplot, we shows the sliding variables s1 and s2, which are become 0. Then the fourth subplot shows the control input to the kinematic model, which are u1 and u2. And for the dynamic model, the input was designed by SMC, which will be discontinuous input. The codes for this simulation can be downloaded from the link given in the description. That leads us to the end of this lecture. Thanks for watching.